Have asked me about determining the equation of a horizontal asymptote in a formal method. So with this particular one, we can see that the degree of the top is the same as the degree of the bottom. They're both degree 1. And the quick way is to divide the coefficients of the highest degree terms, which would be 2 divided by 1 in the denominator, which would give us 2. There is a formal method for doing this, and it's simply to divide top and bottom each term by the highest power of x. Because you're doing the same thing to the top and the bottom, it's fine algebraically. Simplify in the next step. 2x divided by x is 2 plus 1 over x. And in the bottom, x divided by x is 1 minus 3 over x. So remember that we're looking for the end behavior as x approaches positive or negative infinity. As x gets really big, whether it be positive infinity or negative infinity, 1 over x becomes very small, approaching 0. Same thing in the denominator with this 3 over x. It approaches 0. So as x approaches infinity, uh, 1 over x approaches 0, and 3 over x approaches 0. So our expression becomes just 2 over 1. So like 2 plus 0 over 1 minus 0, which is 2 over 1, which of course is 2. So we could put that into our graph we have over here at the bottom right. A horizontal asymptote at y equals 2. Now, we also know that this particular graph is going to have a vertical asymptote at x equals 3. So we'll put that in here. And we can find out what happens near the vertical asymptote. Could use an interval table, but for the purposes of this example, I wanted to talk about whether the graph of the function approaches the asymptote from above or below. And what we can do is if the graph approaches from above, the value of the function, the y value, subtract the equation of the horizontal asymptote, in this case 2. If it's approaching from above, that value would be a positive number because you're taking a bigger number and you're subtracting from it a smaller number. If it approaches from below, you're taking the function value, which is less than this value, and you're going to get a negative. So I'm going to write this out here. So if the value of f at x minus, in this case, 2, is a positive number, the graph approaches from above. If f at x minus 2 is negative, and I'll just write this, then the graph approaches horizontal asymptote from below. So in this case here, we're going to work on this expression right here, f at x. Actually, it's 2x plus 1. So we got 2x plus 1 not writing very well today. 2x plus 1 over x minus 3. And we're going to subtract from that the equation of the horizontal asymptote, which is 2. And we're going to simplify this into one single rational expression. I'm going to put this over 1. We're going to get a common denominator, which is going to be x minus 3. In the numerator here, 2x plus 1 is going to multiply by 1, so that's just going to be 2x plus 1. And then what we're going to do is we're going to have to multiply this denominator by x minus 3. When we expand this out, we're going to get 2x plus 1 minus 2x plus 6 over x minus 3. And that simplifies to 2x minus 2x. They cancel out. We get 7 over x minus 3. So what we've got here is an expression for f at x minus the equation of the horizontal asymptote. As x approaches positive infinity, if you plug in a large positive value here, your denominator is going to be a large positive number. A positive divided by a positive is going to be greater than 0. As x approaches negative infinity, you're going to have a very large negative number, so it's going to be a positive divided by a negative. So kind of summarizing this, as x approaches positive infinity, seven over x minus 3 is going to be greater than 0. Therefore, f at x, the graph, approaches the horizontal asymptote from above. So it's going to go like this. On the other hand, as x approaches negative infinity, we would have a large negative in the denominator, so 7 over x minus 3 is going to be less than 0. So therefore, it's going to approach from below. And that's it for right now.